Hello my dear students, this is Hina Kausar and welcome back to the class. In the previous session, we had discussed regarding Coulomb's law, according to which we learned how the force of attraction or repulsion between any 2-point charges is directly proportional to the product of the magnitude of those charges and also inversely proportional to the square of the distance between them. Also, we came across expression of Coulomb's law in vector form. We defined a dielectric constant, right? And also we learned about superposition principle. Now in today's class, let us try to cover these main topics, that is continuous charge distribution, electric field lines. So let's begin. Continuous charge distribution. What does it mean? It is simple. A system of closely spaced charges will form a continuous charge distribution. But what is the requirement of studying this? It is because, as earlier we had discussed, that is quantization of charges, according to which the charge on a charged body is always an integral multiple of the charge on an electron or a proton. But in practical situations, when it comes to the practical scenarios, the charge distribution, the number of charges on any particular space is very large, right? So in that case, the quantization of charge can be ignored. In other words, it can be said that at macroscopic level, charges can take continuous form instead of discrete packets, as we had said in the quantization of charge. Now, when we consider the macroscopic level, charges can take continuous values of charges. So in that case, the continuous distribution of charge can be one-dimensional, two-dimensional and three-dimensional, which means accordingly it can be either a line or a surface or a volume charge distribution. Now let us discuss in detail regarding linear, surface and volume. Just to calculate the force due to these continuous distribution of charges, right? Let us consider the density of these charges. Linear charge density or surface charge density, volume charge density. Just like in mechanics, as we do considering the mass density or liquid density, right? Ignoring the molecular constituent of that liquid, we just consider the density of the liquid, right? Similarly, let us consider ignoring the elementary charge distribution, ignoring it as the discrete charge packets. Let us consider it as continuous distribution of charge and consider the linear charge density, surface charge density and volume charge density. So if the charges are distributed over a single line, then we call it as line charge distribution, right? And if we have to calculate the linear charge density or line charge density, that is lambda, let us consider two cases. In the first case, I have considered non-uniform distribution of charges over a single line. In a single line, the charges are distributed unevenly, as you can see here, right? In this case, what might be the linear charge density? If you consider a small length element delta L across this line of charges and the charge across the small length element, if you consider it as delta Q, then the linear charge density lambda will be given by delta Q over delta L. But in the other case, when you are considering the distribution of charges over the line is uniform, just like in this example, as you can see, the charges are evenly spaced over a line. In this case, if you consider the length of the charge distribution is capital L and the total charge present in that length of the charge distribution is Q, then the charge density across that length will be given by lambda is equals to Q divided by L. This is how we will consider the density of the linear charge or line charge. How do we define line or linear charge density? For that, we will consider the linear charge distribution. What is linear charge distribution? If the charges are distributed over a single straight line or over the circumference of circle or an edge of a cuboid, etc. Right? In all these cases, the distribution of charges we will consider it as linear charge distribution. Then how do we define linear charge density? It can be defined as charge per unit length, and in SI unit it can be measured as coulomb per meter, right? So what will be the formula we will use to define this linear charge density? For that, let us consider a simple length of charges, right? The positive charges I have considered in a single line, and a small length element across this line of length of charges I have considered, that is dl, and across this small length element dl there will be now a small amount of charges which will be placed, right? According to the definition of linear charge density, lambda will be equal to q divided by L. So in this case, since we have considered a small length element and small number of charges which are present over this small length element, lambda will be equal to dq by dl. Now, just in case if we have to calculate the total charge across this entire line of distribution, right? Then what we have to do, we have to integrate this length element, right? Integrating this small length elements dl and multiplying it with this linear charge density, we will get the total amount of charges which are present across this line, right? So in words, we can write it as q is equals to integral of lambda into dl, that is linear charge density multiplied by all such small length elements. Further, to calculate the force due to this linear distribution of charges, let us consider a scenario here. I have considered a linear distribution of charges in a single line. Let us consider its length is around capital L. Okay. In that line of charges, I have considered a small length element, that is dl, where we can find small amount of charges, that is dq. Okay. Now, the amount of charges which are present here can be written as dq is equals to lambda into dl, which we can consider as equation number 1, right? What is lambda here? Lambda, we know it is the linear charge density across this line. Now, to calculate the force on a charge due to this linear distribution of charges, I have considered a charge q naught which I have placed at point P from this small length element dl, right? Here vector r represents the direction of this force which will be exerted on this charge due to this distribution of charges, right? Now, due to this charge dq, that is lambda dl, we can calculate the force as dF is equals to 1 over 4 pi epsilon naught q naught into dq divided by r square into r cap. This is nothing but the Coulomb's law. We have applied the Coulomb's law and tried to find the force at this point P, which is exerted on this charge q naught due to this small elements of charges dq. Now, what is r cap in this equation? R cap is the unit vector which will give the direction of this position vector r. Substituting the value of dq from equation 1. In this equation, we will substitute the value of dq from equation 1, replacing dq is equals to lambda into dl. In this equation, we will get the force as dF is equals to 1 over 4 pi epsilon naught q naught into lambda dl divided by r square into r cap, where we know 1 by 4 pi epsilon naught is nothing but the force constant. It is nothing but the k, whose value is 9 into 10 to the power of 9. And q naught will be the value which will be given to this test charge, right? And lambda into dl is, lambda is the linear charge density which will calculate for this linear charge distribution, and dl is the small length element which we have considered in the beginning. R is nothing but the distance between this point charge and this length element, whatever we have considered, and r cap is nothing but the unit vector which will give us the direction of this position vector r, or we can say it as the unit vector which will give us the direction of the force which will be exerted on this charge q naught, right? So this is the small amount of force which we will experience due to this small length element, right? If we have to calculate the total force which is exerted on this test charge due to this whole linear distribution of charges, then what we have to do? We have to integrate this term df, right? All such small forces will add up, and that will be the total force which will be exerted on this test charge q naught. So here I have just integrated that term. So total force will be equal to integral of this df, right? Substituting this value from here, after substitution we will get this equation. Since 1 by 4 pi epsilon naught is a constant value, we will remove it out of the integral, and q naught, since we are using a test charge, we will take a constant value, right? So that can also be taken out of the integral. So q naught by 4 pi epsilon naught, integral of integrating lambda dl divided by r square into r cap. Integrating this term, we will get the total force which can be experienced by a test charge due to linear distribution of charges. Let's have a quick review over the derivation. So to calculate the force due to linear distribution of charges, we considered a linear charge distribution of charges of length capital L. In that, we considered small length element dl, where we found small amount of charges dq, which is given by lambda into dl. What is lambda here? That is the linear charge density. That we considered as equation 1. Now to find the force which is exerted by these linear distribution of charges, we placed a charge, that is test charge q naught, at a point P at a distance r from this small length element. After placing it, we observed the force as df is equals to 1 over 4 pi epsilon naught q naught into dq divided by r square into r cap, where r cap is the unit vector which gives the direction of this force. Just replacing this dq value from equation 1, we get the final equation of the force as df is equals to 1 over 4 pi epsilon naught q naught into lambda dl divided by r square into r cap. This is the expression for the force which is exerted due to this small element dl on this point P. Now if we have to calculate the total force due to the total linear distribution of charges, then what we have to do? We have to just integrate this term. After integrating, we will get the equation as vector f is equals to q naught divided by 4 pi epsilon naught integral of lambda dl divided by r square into r cap, where q naught by 4 pi epsilon naught will be constant terms. Therefore, we removed it out of the integral, and we integrated the remaining terms, lambda dl divided by r square into r cap, where lambda is the linear charge density, dl is the small length element, r is the distance between the test charge and the linear charge distribution of charges, and r cap is the unit vector which will give the direction of the force which is exerted on this charge q naught. So this is about the force which is due to the linear distribution of charges. Now the second type of charge density which we have to consider is surface charge density. Usually it is denoted by the letter sigma. Suppose if we consider a surface where the charges are distributed unevenly or non-uniformly, just like this in the picture as you can see, then the surface charge distribution or the surface charge density can be measured as, if you consider area as delta A, small area in that non-uniform distribution as delta A, then the charges which are present in that small surface area will be delta Q. Then the charge density will be, surface charge density can be given by sigma is equals to delta Q by delta A. Now suppose in case if the distribution of charges over the surface is uniform, it means if the charges are evenly spaced, just like in this case, in this picture as you can see. If we have to calculate the surface charge density, then what we will do, we will consider the total charge as capital Q and the surface of the complete surface, whatever we have considered area, as capital A. Then surface charge density will be simply Q divided by A. Sigma is equals to Q divided by D. Can be defined by considering the surface charge distribution. If the charges are distributed over a surface area, then such distribution we call it as surface charge density, right? And the surface charge density can be defined as it is the charges per unit area. Before, in the linear charge density, we considered it as charge per unit length, but since here we are considering the surface, we have to define it as charge per unit area, and SI unit of the surface charge density is coulomb per meter square. Now, to take a mathematical expression, let us consider a surface where uniformly the charges are being distributed. In that uniformly distributed charges, I'll consider a small surface area as ds, where we can find small amount of charges, that is dq. According to the definition of surface charge density, sigma, that is surface charge density, is equals to the total charge per unit area. Now in this case, in this example, the same formula we can consider it. Since we have considered a small surface area, that is ds, then sigma will be equal to dq divided by ds. Now if we have to calculate the total charge over this complete surface, then just like in case of linear charge density, what we did, we integrated the term, right? So here also we will integrate to calculate the total charge, surface integral of this term, that is q is equals to surface integral of sigma into ds, where sigma is nothing but the surface charge density and ds is the small surface area what we have considered in this complete area. I hope you understood what is the surface charge density. Now further, we can also calculate the force due to this surface charge density. Let us have a look at it. To calculate the force due to surface distribution of charges, I just consider a surface where uniformly charges has been. First, what we have to consider, let us consider a small surface element, that is ds, where we can find small number of charges, that is dq. To calculate the amount of charges present over the small surface area, we have to consider dq is equals to sigma into ds. Very simple, since we know sigma is nothing but the surface charge density that has to be multiplied with this small surface area to calculate the amount of charges present in the small surface. So let's consider that as equation number 1. Now to calculate the force exerted due to this surface distribution of charges, I have considered a test charge, that is Q0, which I have placed at point P, which is at a distance r from this small surface element ds. Right? Now according to Coulomb's law, we know that the force exerted at this, on this point charge Q0 due to this charges dq will be given by vector df is equals to 1 over 4 pi epsilon naught q0 into dq divided by r square into r cap, right? So 1 by 4 pi epsilon naught, as you know, it is the force constant. Q0 is this charge which we have considered here, and dq is this charge which we have considered over here, and r will be the distance between these two charges. R cap will be the unit vector which gives the direction of this force. Now, replacing this small amount of charges dq with that of equation number 1, substituting this value equation 1 in the below equation, we get df will be equal to 1 over 4 pi epsilon naught q0 into sigma into ds divided by r square into r cap. Now this is the force which is experienced by this test charge q0 due to this small surface area of charges which is present in this complete surface area, right? But if we have to calculate the total force which is exerted due to this total charges on this point charge, then in simple mathematical term, what we have to do, we should integrate this term, right? On integrating, we get capital F is equals to surface integral of this whole term. I have just integrated this term. Removing all the constant terms from this equation out of the integral, finally we get the equation for the force, the total force due to this complete surface distribution of charges on this point charge Q naught, on this test charge Q naught is given by vector F is equals to Q naught divided by 4 pi epsilon naught surface integral of sigma ds divided by r square into r cap, where Q naught, it is the magnitude of this test charge which we have considered here, and 4 pi epsilon naught, as you know, it's the force constant, and sigma is nothing but the surface charge density, ds is the small surface area which we have considered over here, and r is the distance between the small surface area and the point P where we have considered the test charge. R cap is nothing but the unit vector which gives the direction of this total force which is exerted on this test charge. So this is how we can calculate the force due to surface distribution of charges. Let us have a quick review on this derivation one more time. So basically, to calculate the force due to surface distribution of charges, what we considered a surface area. In that surface area, charges are uniformly distributed. In that uniformly distributed surface area, I considered a small surface, that is ds, where we can find dq amount of charges. Now what is this dq? dq can be expressed in terms of surface charge density, that is sigma into ds. So that we considered as equation number 1. Now to calculate the force exerted due to these amount of charges, that is dq, we considered Coulomb's law. According to Coulomb's law, we found the charge which is placed, that is q naught, which is placed at point P at a distance r from this small surface element. We found that df is equals to 1 over 4 pi epsilon naught q naught into dq divided by r square into r cap. We just replaced this dq term. We substituted the value of this dq term from equation 1 so that we get the final expression as df vector. df is equals to 1 over 4 pi epsilon naught q naught sigma ds divided by r square into r cap. So this is the force which can be experienced by this charge q naught due to this small amount of charges which are present in this small surface element. Now to calculate the total force due to the complete surface charges present in this surface which can be exerted on this test charge q naught, we have to integrate this equation. On integrating, we get this equation, right? Removing the constant terms out of the integral and keeping rest of the terms inside the integral, we get the final expression as vector f is equals to q naught over 4 pi epsilon naught surface integral of sigma ds divided by r square into r cap, and the terms will have their usual meanings. The third type of charge distribution is volume charge distribution, right? And we will calculate the volume charge density to calculate the force due to this distribution of charges, right? Usually the volume charge density is denoted by the letter rho. Say for example, if you have considered a volume like this where the charges are unevenly placed or non-uniformly distributed, right? In that case, you consider a small volume of that complete cuboid or any space, okay, which is of 3-dimensional, right? Let us consider the small volume element as delta V. So the amount of charges which we will find across that small volume element is delta Q. Then According to the definition of volume charge density, it can be defined as rho is equals to delta Q divided by delta V. Suppose in case if we consider the charge distribution over the complete volume is uniform, that is if they are evenly spaced placed on the volume, then we can consider the total charge. The total charge can be considered as capital Q and the total volume we can consider it as capital V. Then the volume charge density can be defined as rho is equals to Q divided by V. In simple terms, how we can define volume charge density? So volume charge density can be defined by considering the volume charge distribution. What is volume charge distribution? If the charges are distributed over a volume, then such distribution we call it as volume charge distribution. And volume charge density is nothing but the total charge per unit volume, and it can be measured in terms of SI unit, that is coulomb per meter cube. Now to understand it in mathematical form, if we have to write an expression for this, let us consider a cuboid which will be having certain volume capital V. In that volume, I have considered a small volume element as dV, where we can observe small amount of charges, that is dq. According to the volume charge density definition, rho is equals to Q divided by V. That is volume charge density is nothing but the charge per unit volume. In this case, what will be the expression? Volume charge density will be equal to dq divided by dV, because we have considered small volume element dV, and in that small volume element we will get small amount of charges, that is dq. Now using this, if we have to calculate the total amount of charges which are present in this cuboid, we can calculate it by integrating this term, that is Q is equals to volume integral of rho into dV, where rho stands for the volume charge density and dV is the small volume element which we will consider in this complete volume, right? Now let's try to find out what will be the force due to this volume distribution of charges. For that, let's consider a cuboid which is having certain uniformly spaced volume charges across the volume. In that, I am considering a small volume element dV which will be having dq amount of charges. Now what is this dq amount of charges? dq can be expressed as rho into dV. Rho is nothing but the volume charge density and dV will be the small volume element which we have considered. Let us consider that as equation number 1. Now to find out the force which is exerted by these volume distribution of charges, let's consider a point charge, a test charge Q0 which I have placed at point P at a distance r from this small element dV. Now it will experience the force. That force can be given by the Coulomb's law, and it is expressed mathematically as vector dF is equals to 1 over 4 pi epsilon naught Q0 into dq divided by r square into r cap, where Q0 is the magnitude of this test charge and dq is the magnitude of the charges which are present in this small element dV, right? Since we have calculated what are the magnitude of these charges in expression 1, we will substitute this value in below equation, right? After substituting, we get dF, vector dF is equals to 1 over 4 pi epsilon naught Q0 into rho into dV divided by r square into r cap, where Q0 is the magnitude of the test charge, rho is the charge density, volume charge density, dV is the small volume element what we have considered, r is the distance between the volume element and the point where we have placed the test charge, and r cap is the unit vector which will give the direction of this force. Now this is the small force which can be experienced by this test charge due to this small element, volume element, right? If we have to calculate the total force which will be experienced by this test charge due to this complete volume distribution of charges, right? Then what we have to do, we need to integrate this expression, right? On integrating, what happens, all such small elements will get summed up, right? All such small forces which can be exerted due to this small volume elements which is present in this complete volume have to be summed up. When how we can sum it up? Just by simple mathematics, that is integration. On integrating, we get the final expression as vector f is equals to volume integral of 1 over 4 pi epsilon naught q naught into rho into dv over r square into r cap. Removing all the constant terms out of the integral and rewriting the final expression, we get it as vector f is equals to q naught over 4 pi epsilon naught volume integral of rho into dv over r square into r cap. So this will be the expression for the total force which can be experienced by any test charge which is placed near to any volume distribution of charges. Let's have a look at the derivation one more time. So initially, we have to consider uniformly distributed charges over a volume to calculate the force due to these volume distribution of charges which will be exerted on any test charge. After considering it, first we should calculate the magnitude of charges which we will consider in a small volume element dV. Right? We have considered a small volume element dV where we can find dq amount of charges which can be given as rho into dV. We considered it as equation number 1. So this is the magnitude of charges which we will find in this small volume element dV. Now we placed a test charge q naught at a distance r from this volume element dV. Here some force is experienced by this charge due to this small amount of charges dq. That force can be given by the Coulomb's law, that is dF, vector dF is equals to 1 over 4 pi epsilon naught q naught into dq divided by r square into r cap, where 1 by 4 pi epsilon naught is the force constant which will take the value of 9 into 10 to the power of 9. Q naught is the magnitude of this test charge which we have placed at the point P. dq is the magnitude of the charges which are present in this small volume element dV. And r is the distance between this volume element and the test charge. R cap is the unit vector which will give the direction of this force which is exerted on this test charge q naught. Now simply replacing this magnitude of the small amount of charges which we have already calculated here in equation 1, replacing it by rho into dV, we get one more expression. So vector dF is equals to 1 over 4 pi epsilon naught q naught into rho into dV divided by r square into r cap. If we have to calculate the total force which is exerted due to this total volume of distribution of charges on the test charge q naught, then we have to integrate this above equation. On integrating, we will get the final expression, that as vector f is equals to 1 over 4 pi epsilon naught q naught into volume integral of rho into dV over r square into r cap. So this will be the amount of force which will be exerted on this test charge q naught due to this volume charge distribution. Let's quickly recall everything. So far we discussed about linear charge distribution, right? Linear charge distribution means if the charges are distributed over a single line, then we call such distribution as linear charge distribution, and the linear charge density is defined as the charge per unit length, right? And it is measured in terms of coulomb per meter, and mathematically it can be expressed as lambda is equals to q divided by L. And also we derived an expression for force which is due to this linear charge distribution of charges, right? So that is given by vector f is equals to q naught over 4 pi epsilon naught integral of line integral of lambda into dl divided by r square into r cap. Similarly, we discussed about surface charge distribution. Surface charge distribution is nothing but the charges which are distributed over a complete surface. That is called as surface charge distribution. And surface charge density is the amount of charges which are distributed per unit area. It is usually denoted by the letter sigma, and it can be measured in terms of coulombs per meter square. Mathematically, it can be expressed as sigma is equals to Q divided by capital S, and the force due to these surface charge distribution can be written as vector F is equals to Q naught over 4 pi epsilon naught surface integral of sigma ds divided by r square into r cap. Similarly, we also discussed about volume charge distribution. If the charges are distributed over complete volume, then we call them as volume charge distribution, and the charge distribution per unit volume is called as volume charge density. It is usually denoted by the letter rho, and mathematically it can be written as rho is equals to Q over V. And the force which is exerted due to this volume distribution of charges can be given by vector F is equals to 1 by 4 pi epsilon naught Q naught into volume integral of rho into dV divided by r square into r cap. Either you can write it in this way, or you can write it as vector F is equals to Q naught over 4 pi epsilon naught. Both are one and the same. So this is about continuous charge distribution. I hope you liked this video. We will continue in the next session. Till then, take care.